I'm Rob MacLachlan, and I'm going to be talking today about some preliminary results we have for a electromagnetic position tracker project that we're starting to develop in Cam Riviere's lab at Carnegie Mellon. This is driven by some of the needs of the Micron project, which Julian talked about earlier, the basic principle of a handheld stabilization tool. And one of the key technologies in order to make this work is that you need a 6 degree of freedom tracker for the hand motion, which is both very fast and has very high resolution. There is a commercial market for position trackers with a similar kind of capability, but their typical measurement rates are in the ballpark of 30 to 200 samples per second, and their workspaces are scaled for conventional surgery rather than microsurgery. Workspaces more on the size of a meter and resolutions of a millimeter. So for Micron, we need resolutions of more like a micron, and we need a sampling rate of something like a kilosample per second. The tremor amplitude drops off significantly above about 10 hertz, but it turns out that in order to cancel this, you need a lot of phase lead so that your cancellation effort is happening at the same time that the tremor is happening. And if you work out the numbers, that you really can't have a system loop delay of more than a couple milliseconds. And that means that the position measurement part of this system shouldn't really take more than like a millisecond. So because of this, we developed our own position tracker, which is based on the PSD technology. It's a rather old analog position sensing detector that can measure the centroid of a spot. And using this, we were able to achieve the speed and resolution performance, but the workspace is pretty small. And also, like all optical trackers, you have to have a clear sight line. So I showed an electromagnetic tracker on the first slide. One of the technologies, in addition to the optical triangulation, like in our ASAP sensor, is electromagnetic tracking. It's fairly easy to scale up the speed of an electromagnetic tracker, but that also increases the noise. And if you look at, you can define a figure of merit for the speed of a tracker in terms of the square root of bandwidth divided by the noise. And we need about 20 times better than the best commercial electromagnetic tracker, which is a pretty significant increment, but we've already achieved a factor of 6-fold in our current prototype, and we think we can get another 3-fold once we do our custom electronics and so on. So this is part of the new in-loop electromagnetic tracker project that we're starting. And in addition to developing a tracker that's going to meet the needs of Micron, we've also told our funders that we're going to develop an open tracker design that other people can use and adapt. We're going to make available all of the hardware and software designs, but also we're going to develop what we call a reference design, which is sort of a standard, straightforward implementation of an electromagnetic tracker. It's like if you start out with a reference design, you're basically playing on the easy setting, and then once you've figured out whether an electromagnetic tracker can do what you want, you can customize it to your particular application because it's an open design. Electromagnetic trackers have been around for 40 years now, and the technology itself is not tremendously difficult. Many people have reinvented it. Some of them have been incorporated in products or used in research, but on balance, optical trackers are more popular because they have better accuracy overall. So how does an electromagnetic tracker work? Well, you have to establish several magnetic reference fields, and then you have a probe which measures those reference fields, and then you can solve for the position of the probe by using the magnetics model. Since we need a very high speed, we're transmitting all 3 reference fields simultaneously and are using frequency-domain-multiplexing, transmitting each field at a different frequency. EMTs don't require a sight line, but they do have several of their own particular problems that they can be interfered with from high conductivity materials or magnetic materials, which mainly means metal, but they are not interfered with by any kind of insulating material or the human body. Another problem with EMTs is electromagnetic interference from the power system and high power devices. So in particular, I'm going to talk today about electromagnetic interference that's in the form of impulses that say, you know, when some machinery switches on, you may get a big pulse in the system, you know, which an electromagnetic glitch, which can cause the tip of your instrument to twitch if you believe that this, you know, is the real motion. So it's difficult to, with a frequency domain technique, impulses are a problematic kind of noise because it's spectrally broad. If we look at the spectrogram there, that, you know, at about 5 milliseconds, an impulse happened and it corrupted, you know, the amplitude in all of our measurement channels, which range from about 7 to 13 kilohertz. So, well, although it's spectrally broad, it's well confined in the time domain, and that means that it also, in order to have enough energy to be a problem, it has to have a higher peak amplitude than the normal white noise floor. So you can potentially detect it by being basically an outlier, but in order to do that, since the signal to noise of the system has to be very high in order to achieve the kind of dynamic range of measurement that we want, that the impulse may still have an amplitude which is way below the signal amplitude. So you have to have some idea of what signal you're expecting to see in order to determine whether there's an outlier or not. And well, what's a technique where you predict what you're going to see and then look at the mismatch between that and then use that to update your estimate? The Kalman filter is an obvious time domain approach to do there. And if you just, so you know, you have your input signal and comes in here and you subtract your predicted model from it and then you use the mismatch between the prediction and input to update your idea of the state that you output. And also you have the dynamics of the filter determined by the noise model, and you can update that noise model if you have additional information. And in fact, in our frequency domain system, we have good information about whether there's a presence of the impulse because we allocate guard channels between each of the bands, and if there's something in the guard channel, that tells us that there's probably an impulse going on, or at least there's interference, so we should dial back our response to this particular sample. And that actually works pretty well at suppressing impulses, but the effect is basically, if you have an impulse, you kind of coast through just riding on your prediction, and you don't make use of any of those measurements. It occurred to me that another thing that you could do is you could adapt the Kalman filter to make it dual rate. So we have our samples that are coming in here at 96 samples per second, and then we, you know, do a 64-point FFT to find what's going on in the channels, giving our 1.5 kilosample per second output. But this demodulator is actually embedded inside the Kalman filter feedback loop here, so that the subtraction here takes place at the high sample rate, and then the prediction takes here after the demodulator. Down here is used to make the carrier model, which is upsampled and subtracted from the input. So when you do this, here's an example of this is the input signal that's coming in, and believe it or not, this has actually been corrupted by an impulse. The problem is that the impulse is 40 decibels below the signal level, so you can't even see it in this plot. And each dot here is a 10 microsecond sample on the input. Now, if we look at the residue here after the subtraction, we can see, sure enough, there is this impulse disturbance here, which is way above the level of the residue here. You know, what we're expecting to see is down close to 0, and there's a little bit of white noise down here, but this is like, it really sticks out. And you can use a quite simple thresholding algorithm where you just identify when it goes above the threshold and then, you know, find a window and make the window a little bit wider and zero it out in that area. And then you basically cleaned up the residue here before you go into the demodulator so that this impulse does not get spread out. And we have about 8 samples here that have been corrupted. That's like about 80 microseconds of our 700 microsecond sample period. So we still have like 90% of our data left. And here's the spectrum of the residue that I showed in the beginning. And here's after cleaning up the impulse. And here's the demodulated output if you don't have the impulse blanking. And then the green line is with the impulse blanking. You can see that it's hardly excurs above the noise floor. So any questions?